Nuclear binding energy is the energy required to disassemble a nucleus into its constituent unbound neutrons and protons. In other words, it's the amount of energy you need to completely split apart your nucleus into individual nucleons. It's also the amount of energy that would be released when the nucleus is created from its constituent nucleons. So if you took a whole bunch of protons, neutrons, stuck them together to create a nucleus, then there would be a whole bunch of energy released. That total energy is known as the binding energy of the nucleus, or the nuclear binding energy. So it's equal to the mass defect between the mass of the whole nucleus, the nucleus as a whole, and the sum of the individual nucleons converted into energy using E equals mc squared. So m being the mass defect, c being the speed of light. So basically, the mass of the whole nucleus will be less than the mass of all the individual parts that make it up. Now, obviously, the bigger the nucleus, the bigger the total binding energy will be for that nucleus. So if I'm only putting together a helium nucleus and it only requires 4 nucleons, 2 protons, 2 neutrons, that's not going to release as much energy as if I was to make a uranium nucleus with 235 nucleons. So the bigger nuclei have a higher total binding energy than smaller nuclei. So if we want to compare different nuclei, then actually what we have to do is look at not just the total binding energy, but the binding energy per nucleon. In other words, we take the total binding energy and we divide it by the number of nucleons in the nucleus. And that way we have a comparison per nucleon for each particular nucleus. And that's the investigation you're going to look at in today's lesson. There's a link in Google Classroom to this worksheet. So I've broken you down into groups. So each one of you is going to look at 8 different nuclei. So I'll take Yu-Yang for example. So if I was to look at the element with proton number 8, what I'm going to be looking for is the most stable, naturally occurring nuclide. Okay, and when I find that nuclide, I'm going to put the nucleon number in here, and I'm going to put the binding energy in here, and I'm going to get this information from the periodic table of the elements on Hyperphysics that is also linked on Google Classroom. So going back to Yu-Yang, so what I'm looking for is the element with proton number 8. So the proton numbers are up here, 1, 2, 3, 4, 5, 6, 7, 8 is oxygen. Now, I'm not too interested in the top level chemical information, so I'm going to look at the nuclear data for this. Okay, and we can see there are a number of different nuclides we could have of oxygen. We could have oxygen 13, 14, 15, 16, 17, or 18. But what we want to look at is which is the most naturally abundant, stable nuclide. So looking down here, 99.7% or 99.8% of oxygen is oxygen 16. Okay, so the most stable, most naturally abundant nuclide of oxygen is oxygen 16. And the binding energy of oxygen 16 is 127.62 mega electron volts. So if I copy that back into here, I can say, okay, the most stable naturally occurring nuclide is oxygen 16. The nucleon number is just the 16, and the binding energy is what I copied from there, 127.62, and when I return that, this will automatically calculate the binding energy per nucleon simply by dividing the total binding energy by the nucleon number. And so we get 7.98 mega electron volts. Okay, that's a fairly straightforward one. some of them are a little bit more difficult. What I've done is I've given you all one example so you've got something to copy from. Apart from this one here, which is Sam's, okay, because this one's a little bit more tricky. So I'm going to look at number 86 here, proton number of 86. So I'll go back to my hyperphysics periodic table, and 86 is radon down here. Okay, again, not so interested there, so I'm going to look at the nuclear data, go to the nuclear data, and what we can see here is that there are no naturally abundant nuclides of radon. So to look at the most stable ones, what we have to then turn to is the half-life. And the most stable will be the one with the longest half-life. So this is 2.4 hours, 14.6 hours, 24 hours, 25 milliseconds, 0.27 milliseconds, 3.96 seconds, 55.6 seconds, or 3.823 days. Okay, so days is the longest here, so our most stable nuclide of radon is radon 222. Okay, and the binding energy of that is 1708.2. So I'm going to copy that. And 86, we've got radon 222, nucleon number 222, and the binding energy of 1708.2 mega electron volts. Okay, so we work out the binding energy per nucleon there. Okay, as we go through, some of these are a little bit more tricky, particularly as you get to the higher numbers. There are basically the isotopes that have existed are very often made by humans, and they don't last very long, and certainly not long enough for us to determine any properties from them. So it may be the case that there are absolutely no stable isotopes whatsoever that we know anything, stable nuclides that we know anything about. In which case, just put the word none in there and leave everything else blank. It may also be the case, like here, where the hyperphysics periodic table only goes up to 103. Okay, so anything above 103, you're really going to have to look elsewhere to see if you can find the information. And again, if you can't find that information, if there are no stable nuclides of any particular element, then you just put none in here. Okay, now this is a real collaborative effort. Everybody has to do their part. And what you'll see is once everybody's done it, we can look at the binding energy per nucleon graph. Is a graph literally of binding energy per nucleon up the y-axis and the nucleon number on the x-axis. And what this will do is this will automatically adjust and plot the data as you enter it. So once everybody's done their bit and everybody's done their 7 remaining nuclides on here, then we'll be able to see if there are any patterns or trends on this graph. And what we'll do is next lesson on Tuesday, when we have our next synchronous lesson, we'll discuss the results of this, as well as the graph of stability, which will start to build up as you put more and more data in here as well. Okay, so those are 2 graphs for you to look at once you've put your data in for the binding energies for the most stable naturally occurring nuclides where possible for each element of the periodic table.